All right, thanks so much for checking out the video. It's great to be here at ISPD, coming at you virtually from inside of Carbon Nanotube. Today I'm very excited to present our recent work on transforming carbon nanotube technologies all the way from a low-level transistor up to a full microprocessor level. And I've highlighted some of my colleagues here who have been heavily involved in this work at MIT. And then I'll also be joining Harvard in the fall, and we'll continue some of this work there as well. So I'll start this 15-minute presentation with a question that I often ask myself. We all know that electronics has improved dramatically over the years. How much more can it really improve? And the reason why I ask this question is because electronics are not only facing one wall, they're facing multiple walls simultaneously. So as many of you know, there's the miniaturization wall, where it's getting harder and harder to cram more transistors into a single chip. There's the power wall, where scaling these transistors is no longer giving us the same energy efficiency benefits. There's the memory wall, which is driven by applications, where a computing system today can spend the vast majority of its execution time and energy just passing data back and forth between a processor chip and a memory chip without even doing any useful computation. And the list of walls goes on. So to overcome these significant challenges, the answer lies in realizing transformative new nanosystems, which leverage the unique properties of many energy-efficient emerging nanotechnologies to build entirely new system architectures. And only by overcoming inherent imperfections and variations and fabrication challenges with these new technologies can we experimentally realize these next-generation computing systems, for example, with three-dimensional system architectures that have multiple layers of transistors, multiple layers of memory, or multiple layers, even sensors or other types of technologies that are all fabricated directly on top of each other, all over the same starting substrate to overcome these system level bottlenecks that I mentioned, for example, like the memory wall. And these types of systems are going to drive the next generation of energy efficient applications. So to put this as a little more of a concrete example, here's an example of what a future nanosystem might look like, with multiple layers of computing logic built directly on top of each other, with interleaving layers of memory and very dense, ultra dense vertical connectivity spanning these multiple layers, truly embodying this computation in memory approach. And more importantly, this type of chip would be very challenging or maybe even impossible to build with conventional silicon-based technologies. So to build these nanosystems, we need to focus on promising nanotechnologies. And there's a few different ones that, that can be used to build these next generation systems. But one of the ones we focus on in our lab is carbon nanotubes. There's a couple of reasons why we use carbon nanotubes. One is that they make very, very energy efficient VLSI circuits. And another key property, which is one that I'm probably even more excited about, is that CNFETs can be fabricated at low processing temperatures, below 400 degrees Celsius, which is a key property that enables these monolithic 3D systems where multiple layers of carbon nanotubes can be fabricated sequentially over the same starting substrate. So here is an illustration of a carbon nanotube FET, field effect transistor, similar to a silicon MOSFET, except you take the semiconducting channel, which is silicon, and replace that with carbon nanotubes. And so ideally you want all of these carbon nanotubes in the channel to be semiconducting. I'll get into that a little bit later. But then you also have these traditionally defined source, gate, and drain regions to make up the carbon nanotube FET. But despite all these promises of CNFETs, there's always a catch. And the catch here is that it can be very hard to build working systems because with many nanotechnologies, they suffer from major imperfections and variations. So for CNTs, I've highlighted a few of the challenges here. On the left are material level challenges. For example, the presence of metallic CNTs, which are CNTs that have a very small band gap, and so you can't modulate them very well with the transistor gate, so they lead to increased leakage current in your circuits. Another is manufacturing type defects, and here I'm showing an aggregation of multiple CNTs, that have bundled together on the wafer, forming a defect that would reduce yield. And then the last one that I've highlighted here is how to realize a CNT CMOS process, or a complementary MOSFET process, with both PMOS CNFETs and NMOS CNFETs. This is a challenge for many emerging nanotechnologies to realize. CMOS, which is required for making energy efficient digital logic circuits and the static CMOS circuit family that we conventionally use today. So to overcome these significant challenges, I'll summarize some of the key processing and design techniques we've developed, which have really been essential for demonstrating the large scale systems that I'll show you. So I'll take these in turn. The first is to deal with the manufacturing level defects. So here you can see a zoomed out image of CNTs that are deposited across the wafer. And then these little black dots are the bundles that I showed you in that last image. So we've developed a selective exfoliation technique. This is called rinse in the paper. Removal of incubated nanotubes through selective exfoliation. But so in rinse, what we do is we sonicate the wafer, and then that reduces the number of defects per unit area by a factor of 250x. And then all the circuits that we fabricate on top have no damage to them. The next challenge I'll just briefly describe is how to realize the CNT CMOS process. There's been many approaches to realizing CNT CMOS, but it's been challenging to find one that has a couple key characteristics. Some of these should be solid state, also air stable, can be silicon compatible, which means that you can take CMFETs and integrate them directly on top of silicon circuits or a silicon substrate. Ideally, it should use existing equipment, for example, for metal deposition or oxide deposition. And it should result in reproducible and robust CMFETs across the wafer. So here is an illustration of our technique called mixed, which stands for metal interface crossed with electrostatic doping. It's a combination of using different work functions for the PMOS CMFETs, which are highlighted with the green contacts there. The green is platinum metal. And then for the NMOS, we use a relatively lower work function metal, which is titanium, for the blue contacts for the NMOS CMFET shown on the right. And then we also use different oxides for the PMOS and NMOS CMFET, which helps to electrostatically dope the channel and realize these complementary ID-VDS curves shown on the right. So to highlight the reproducibility of these, this is 1,000 different NMOS CMFETs and 1,000 different PMOS CMFETs taken from across the wafer. And there, for all these ID-VGS curves, there are no CMFETs that have been omitted. But one thing you might ask is, okay, what's up with some of this extra leakage current for some of these devices? And that's because of what I alluded to earlier about metallic CNTs. So metallic CNTs make up a small fraction of the total number of CNTs and increase leakage current because they can't be well modulated by the gate. So I'll go into a little bit more detail here because I think it will be interesting for the ISPD audience. So as a quick background in metallic CNTs or MCNTs, here is an idealized CMFET where all the CNTs are drawn as semiconducting or SCNTs, meaning that they make these nice transistor channels that you can turn on and off with the CMFET gate. But unfortunately, because of our sort of imprecise control over atomic scale CNT properties, a small fraction of these CNTs are metallic, meaning that they have little or no band gap, and so you can't turn them off well with a transistor gate, and they're still going to leak current. So these essentially act like small metal shorts inside your circuit, which is obviously undesirable. So because of these challenges, we sort of went back to the drawing board to see what are the alternatives with dealing with MCNTs from a pure processing point of view. And ideally, the best option would be just not to grow any MCNTs. And even though many people have tried, this is still an outstanding challenge. So instead, there's another option where you can actually buy right off the internet pre-sorted CNT solutions, which have most of the metallic CNTs are already removed before you buy the CNTs. And with thousands of papers on this topic of CNT sorting, the best purity that people have achieved is somewhere around 99.99% semiconducting CNT purity, or 0.01% metallic CNTs, which means about 1 metallic CNT and about 10,000 CNTs. So yeah, that sounds pretty good. But then we ask ourselves, what are the requirements for actual VLSI circuits? Is 1 MCNT and 10,000 CNTs, is that good enough? Or is it already way too good? Or does it need to be way better? So to answer this question, we need to quantify the impact that MCNTs have at the circuit level. And there's 2 main cases that we need to analyze. One is that because MCNTs increase the leakage current, this translates to an overall increase in the energy consumption, which degrades the energy efficiency benefits, and that's part of why we wanted to use CMFETs in the first place. And second, shown on the right, is that MCNTs also degrade the transfer curves of logic gates, which can be even worse because this can lead to incorrect logic functionality in your circuit. For example, you measured a 1 when you're expecting a 0 or vice versa. And I want to just take a couple minutes to show you how we quantify this degradation using a metric known as the static noise margin, because this turns out to be the limiting factor for what level of MCNT purity we need. So the static noise margin is defined basically for every pair of connected logic gates inside your entire circuit, because it's not enough for the individual logic gates to be functional, but they also need to be cascadable, meaning that an output 0 or 1 from this driving logic gate needs to be able to cause an output 1 or 0 in the loading logic gate. So the noise margin tells you whether or not these gates are cascadable, and then also how much noise they can tolerate. So to measure to quantify the static noise margin, we start by measuring the transfer curves for each one of these logic gates, which is the output voltage as a function of the input voltage. And then then we extract these points on the curve where the slope is equal to -1, which you can see here with the dots. And then you can see the noise margin by looking at the butterfly curves, or eye diagrams, some people call them, between the transfer curve of the driving logic gate and then the mirrored transfer curve of the loading logic gate, where the noise margin corresponds to that size of the box that you can draw inside. And then here are the equations for reference. So when we start to add metallic CNTs, you'll see these transfer curves start to degrade. So here are those exact same transfer curves, but this time shown for a NAND gate driving a NOR gate. And as we add metallic CNTs, this will be for one metallic CNT, we see that the transfer curves start to degrade and the noise margin starts to shrink. If we add another metallic CNT, now the noise margin completely vanishes, which causes a noise margin violation, which leads to incorrect logic functionality. But that's just for one pair of connected logic gates. Inside an entire VLSI circuit, you obviously have many pairs of connected logic gates, and we need all of them to meet some minimum noise margin requirement. But due to the CNT variations in metallic CNTs, there's a finite probability that that's not the case. And that is what we call the probability of noise margin violation, or PNMV. And this PNMV is a probability that any pair of connected logic gates inside the entire circuit fails to meet some minimum noise margin requirement. And this is what we use to figure out what level of MCNT purity we need. Okay, so after all that, here are the results. We find that we need a purity of about 99.999999% purity, which corresponds to about 1 metallic CNT in about 100 million CNTs, which is still about 4 orders of magnitude off of that best result I showed, or that I told you before, of about 1 MCNT at about 10,000 CNTs. So today I'll show you a new design technique called DREAM, or Designing Resilience Against Metallic CNTs, which overcomes this presence of metallic CNTs entirely through circuit design and lets you yield VLSI circuits using CNT purities that you can literally buy on the internet today. So the key to DREAM is realizing that MCNTs affect different logic gates differently, depending both on their circuit topology and also on their physical layout. So here we have those same transfer curves I showed you before, where we get a violation when the NAND gate was driving a NOR gate. And the trick with DREAM is that specific combinations of logic gates are more susceptible to MCNTs. So even by using the exact same transfer curves, I haven't changed the transfer curves at all here, we get a violation when a NAND gate drives a NOR gate, but it's okay for a NOR gate to drive a NOR gate. It's also okay for a NAND gate to drive a NAND gate. So we can still use both NANDs and NORs as long as we avoid these bad combinations. And so the DREAM solution is to first identify these bad combinations and then apply a logic transformation during logic synthesis to avoid these bad combinations of logic gates while still maintaining the same overall logic functioning. And this is compatible with existing design automation tools for logic synthesis. There's also a detailed methodology in the paper and in some of our other references to show which combinations of logic gates to use and with what probabilities. and I won't go into all those details today. So now we have these new nano design techniques and nano fabrication techniques, mixed, rinse, and dream. But the question is, do these techniques work experimentally? And so this brings me to one of our most recent experimental demonstrations, where we've experimentally demonstrated a RISC-V microprocessor built entirely out of CNFETs. So this is an actual photograph of the die. It's actually stitched together from over 6,000 individual pictures that we took on our automatic probe station, and then stitched together similar to how your phone would stitch together pictures in a panorama. So because it's all these individual pictures, you actually zoom in, see the individual power rails going across, individual routing traces, logic gates, CNFETs. You can see the NMOS CNFETs with the titanium are in the sort of brown color there. The PMOS ones have platinum, which is, shows up as being sort of white here. And then the CNTs are inside the transistor channel. They're too small to see optically. So we worked with our collaborators, architectural level collaborators at MIT to make RV16X Nano, which is 16-bit implementation of a standard RISC-V instruction set. This runs 32-bit instructions on 16-bit data and addresses. Has over 14,000 complementary CNFETs, both PMOS and NMOS, with millions of total CNTs inside the channels, and over 80 stages of cascaded digital logic. And importantly, it's all designed using standard VLSI processing and design flows. So here's a 3D rendering of the GDS layout that we created for RV16X Nano. I also want to highlight that as part of our VLSI design flow, we created a full CNFET process design kit for our process at MIT with experimentally calibrated compact models that work with existing circuit simulators. Then there's also full design rule check, layout versus schematic, parasitic extraction. They're all compatible with existing tools for design automation from Cadence, Mentor Graphics, Synopsys, etc. So I also created a full standard cell library for CNFETs, which we use with Cadence Genus in this case to synthesize the Verilog description of the processor into logic gates, using Dream to overcome the presence of metallic CNTs. And then the placement route was done with Cadence Innovus. So here are some of the experimentally measured waveforms for RV16X Nano. The input instruction is shown in the top in blue, and the output character is in red, where I've converted the binary waveforms into hexadecimal. And then to make it even easier to read, translated this into ASCII characters. So you can see this is the canonical Hello World program. But of course, the goal here isn't just to run Hello World. Instead, the key takeaway that I want you to go home with is to realize this new level of technology maturity that we can achieve by coordinating advances in both nanofabrication and nano design. So RV16X Nano is fabricated across full 6-inch wafer substrates. It leverages existing infrastructure for both processing and design. And importantly, it's achievable today because we're using techniques in nano design, such as Dream, also techniques in nanofabrication with rinse and mixed to overcome variations in nanotechnologies. I also just want to quickly mention that CNFETs aren't just limited to digital logic, but similar to any type of MOSFET. They can yield analog circuits or SRAM. CNFETs can be integrated on top of silicon CMOS. They can also integrate with sensors or be used as sensors themselves. In the bottom right, I'm showing a demonstration where we fabricated CNFETs directly on top of an imager to run image processing logic directly on top of the pixels that are capturing the image. So you can learn more about some of these systems in paper at ISPD, and then also in some of the references that it points to. So I'll wrap up by describing just quickly some exciting directions that are going on right now, where we're transferring the CNFET process into a commercial foundry at Skywater Technology Foundry. This work's being done as part of the DARPA Three-Dimensional System on Chip, or 3D SoC program, where we're transferring these technology for these monolithic 3D integrated systems that I talked about earlier. And in this case, have multiple layers of CNFETs and multiple layers of resistive RAM, which can also be fabricated in the back end of line, that are all fabricated in the same sequential three-dimensional stack. So with that, I want to thank all of our sponsors and collaborators who we've worked very closely with. Also want to thank all my fellow group members in Novels Electronic Systems group at MIT. Also like to thank everybody that we've worked with as part of DARPA 3D SoC. And would like to thank all of you for your time. And I hope you come to our session on, I think it's session 8 on Tuesday. And I'd be happy to answer any questions there. Thank you.